Thanks, Terry. That was very informative, and as you can see, it's a little bit of a minefield. It's opened up. I think it's something, as switchboard manufacturers, we talk amongst ourselves daily about this with our staff, and that what do we do here, what do we do there. There's a lot of anomalies with switchboards that are creeping up. David brought up quite a few, and Terry's actually probably opened up another can of worms for us. Thanks, Terry. Especially about Section 4. I wasn't aware that metering was going out of the. Thought it was just being revamped, but that's interesting. Our next presentation is titled "The New AS3000: What It Means to Switchboards," and will be presented by Scott Emerson from Controlling Power. Scott joined NESMA New South Wales in 2005 and held the position of secretary for 8 years. Then we kicked him off and made him the president. He's the current president. He also sits a sitting member of the EL68 Standards Committee, responsible for the new NZS 61439 switchboard standard. A licensed electrical contractor and holding an advanced diploma in electrical engineering, Scott is also a counsel in the New South Wales Business Chamber and enthusiastic about promoting Australian manufacturing and Australian designs. Responsible for drafting some of the new diagrams in the new switchboard standard, Scott publishes articles on LinkedIn, which is another, we're going to add that onto our website eventually, promoting understanding of the real-world details from in specifying and construction based on the standard. Scott is the Director of Controlling Power and Manufacturing Switchboards here in Sydney. Welcome, Scott, to the stage.
Good morning, everyone, and thanks for giving up your mornings. I'll try and be brief with the 2 minutes that I've got left now. Thanks, Terry. And Tony, you never fail to disappoint us.
I've got a question for you, Scott.
I haven't even started yet.
Has NESMA had any representation or input into what's happening with the revision in regards to smart meters?
We've tried. NESMA has a number of representatives in different committees with EL1, EL68. Sean Peacock from KE Brown is our representative on the service rules, and I know it's a fairly, like EL1, it's a fairly diverse group of people that Sean gets to deal with, and there are challenges met every day in those meetings. So we do try. The success is sort of shown in some of the outcomes, but we'll have to sort of wait and see what the next stage of the service rules is. As I said, I've got 2 minutes now left, Tony. Thanks for that again. We're going to talk about the new AS3000. Now, I've got in 2017 here in brackets. This is not necessarily the release date. The EL1 group that puts this together, again, as I said, is quite a diverse group with many different interests in the industry. The public drafts have been released and had public comment returned. What we're essentially left with is a document that's just being ticked off, ready for publication. But the slow time frame in standards sometimes means that takes a little longer than expected. So we're hoping this year, but it may not actually make it quite through. So we're just going to look at the key changes, and I've focused on a couple of points. There are a number of changes in AS3000, and I tried to pick the ones that are going to be most relevant to switchboards and the most informative. So we've got clearances around switchboards, separation of switchgear. Some of these are quite small points, but quite relevant. Date of initial energisation, and Appendix K. Now, I don't know how many of you remember the lovely old yellow AS3000 1991. We had a Table C1 and we had an Appendix J. The document then since got a little bit smaller with AS3000 2000, and fortunately there's been some bring back into this more informative style of publication. So let's just start with clearances. This is a fairly significant change for us as switchboard manufacturers and for a lot of the specifiers in the room. There's now a 1 metre minimum clearance from all accessible faces of the switchboards, where it used to be a 600 clearance. This is not from the sides, this is only from the usable faces. An unimpeded space of at least 600 around the switchboards. That's pretty much standard as what was in place before. Openings and doorways are at least 900 mm wide and 2200 high. Now that's a big one if we all look at the switch rooms these days, that the building was sort of slab was poured, the switch room was laid out, the switchboard was put in, and then the room was built around it, makes it very difficult to get these things out. Where switchboards are located opposite one another, the clearance shall be measured with only the widest door in the open position. This is always a bone of contention in previous standards, where it wasn't clear whether you had to open two doors facing each other. And we'll just have a look at some of these diagrams that are now in the standard. So as you can see with this one, we've got 600 from all of the projections as an absolute minimum. 1 metre from the usable face. Now the top right there you can see an air circuit breaker that actually projects beyond that usable face of the switchboard. The 600 clearance, minimum clearance, is from that projection of the circuit breaker. If the 1 metre from the usable face is further than that, then the 1 metre takes precedence. It's a fairly informative diagram. As you can see, the withdrawn section, the bottom left, is a rack-out switchgear. Still has 1 metre from the usable face, the closed face of the switchboard, but 600 clearance from the racked-out position. Here's another example where we've got two switchboards facing each other, and this was one of the issues that we always had. Some inspectors would issue defects where we had two doors open at the same time and they required 600 clearance between them. That's no longer the case. The likelihood of working on both switchboards at the same time is quite low, and they've accepted that you can do this 600 clearance with only one of the doors open, but you should choose the widest door. Restructure of the safety services clause. This is only a small one, but I think important to a lot of people. Clause 7232 switchgear. Where safety services are installed, all switchboards that are required to sustain supply to safety services shall be constructed so that the safety services switchgear is separated from the general switchgear by metal partitions. Now, one of the things that used to be possible is that you could provide separation that wasn't with metal partitions. They've clarified this now. A non-metallic case of a switchboard does not comply. Now, you might see some smaller assemblies that had a lift circuit effectively off a distribution board, and you might have wanted to put that into some kind of polycarbonate centre to separate that. That's no longer permitted. It must be its own section. Date of energisation. Again, just another small one, clause 8.4. The date of initial energisation or certification of an installation shall be available on site. So we currently have a date of manufacture on most of our 61439 or 3439 labels. This is a date of energisation. This would be an interesting little trick that we may have to supply some extra labels after the switchboard's been installed, but from a manufacturing point of view, just a little one to remember that's made its way into the standard. So Appendix K, and this is probably the big talking point that's been reintroduced that was very similar to Appendix J in the old AS 3000. Basically we've got is, we're focusing on the clause deemed to comply, current rating by testing, rated diversity, verification assessment and device substitution. And we'll just touch on all of these. So firstly, deemed to comply. Basically what this means is that Section K is not a substitution for 61439 or 3439. We're talking about introducing some of the clauses into AS 3000 that make it easier to reference back to 61439 for understanding. So if you comply with 61439, you're deemed to comply with these clauses in AS 3000. Current rating by testing and temperature limits. So clause 10.10 and table 6, both in 61439, provide requirements which are to be satisfied for the current rating of a switchboard. Oops, jumped one. This is also related to the current carrying capacity of outgoing circuit, so the INC, the maximum demand after rated diversity. So these are little things that you might see in specifications where a rated diversity is listed. This clarifies some of these in terms of calculations. So we've got an example in the back now with Appendix K. If we assume that INA, there's 1600 amp switchboard, INC is the maximum rated current of an individual circuit. Now we must accept that the IN rating of an individual circuit breaker, let's take a 630 amp circuit breaker, may not be 630 amps when it's put inside a switchboard. We've got a derating factor depending on air movement, copper connection onto the breaker, the ability for that to dissipate heat. So in this situation, this calculation, we've got an INC of 534 amps, which is a D rating of 0.85. So the rated diversity factor divided by the assumed loading factor. So here we have a rated diversity of 0.9 in this calculation. This is the example in the standard that you can refer to. 0.9 times 534 amps, which is the D-rated rating of that circuit, gives you a total rating of 481 amps per circuit. And that's giving us a 0.9 rated diversity. Now, if we've got a 1600 amp switchboard in this situation, we can pull our rated diversity up a little bit. We can't go past our nominated rating or a D rating of our circuit breaker. So if a system is tested, however, let's call it 1890 amps, has three individual circuit breakers at 630 amps. These have been temperature tested and require no additional D rating. And we may have a rated diversity of 1 because we've got a main bus of 1890 amps. There's no reason why we haven't got a rated diversity of 1 and a fully rated system. If this assembly had a tested bus bar at 1600 amps, but we had no further D rating for temperature of the circuit breakers, then your rated diversity would be 0.85. So I hope that's not confusing too much. We've got lots of D rating factors involved, but essentially the first one to look at is the rating of the circuit breaker and how it's D rated in its assembly, and then a further D rating for diversity. Verification assessment. So clause 10.10.4 provides information on this calculation procedure. A lot of the details are still referred back to 61439 or 3439 for tables or appendices. So appendices H and N provide operating current and power loss of the copper conductors and also refer to 60890, which is a temperature rise calculation. So here's an example of table N. So this is put back into 61439. We don't have table C1 in AS3000 still, but this is quite a conservative rating of copper bus bars inside an enclosure. Further to this, if you've done verification, you may end up with better results out of calculation. You may end up with better results again out of test. So verification assessment is when we're using calculations to come up with our temperature rise in this situation. The ratings of the circuits are limited to 80% of the rating of the device. So what you must understand is if you've got a 250 amp breaker and you're going to provide a temperature calculation, you can't go past 200 amps for the rating of that breaker. That may give you better results on your rated diversity, but you can't go past that D rating. Verification by test may give you higher ratings than the verification assessment for the same bus bar rise as well. Device substitution. Now this is a hot topic that's gone backwards and forwards in the 61439 committee for several days. Good luck is the beginning of that one. We cannot simply accept that two different devices will perform the same way. While temperature rise calculations from test is not difficult because most manufacturers provide watts losses from each circuit breaker, so it's quite easy to say that this one has a lower watts loss. We can position that in the same way and accept that our temperature rise is going to be acceptable. It's based on the same size or arrangement of compartments that have been tested to arrive at that original temperature. Performance on a short circuit or arc fault can be quite different. As I said, watts losses on a single break device might be lower than those on a double break, but its performance under short circuit may be poorer. Arc vents on breakers may be in different positions, and gas expansion may vary. So when can I do this? A device may be substituted with a similar device that is used in the original verification, provided that if the device is not from the same manufacturer, it does not exceed 3150 amps. So if you're going to go over that rating and do some 4000 amp devices, then basically you have to test. The power loss and terminal temperature rise of the device are the same or lower when tested in accordance with the relevant product standard. So that's one that would have to refer back to the manufacturing data. And the physical arrangement, the functional unit is the same. And the requirements of the device manufacturer are complied with, and the device manufacturer declares the performance characteristics to be the same or better in all relevant aspects to the series used for verification. So if we're talking about device substitution from one range of a supplier to a newer range that's coming out, then you're likely to get that device manufacturer provide you the data that says that they are as good or better than the previous range you tested. Device substitution under that situation is quite simple. But if you're going to change brands, it's very difficult to get one manufacturer to nominate that their product is going to be as good or better than whatever it was you tested. And that's where the trick is with device substitution. So what we're saying is, if you want to maintain full compliance with this document, you need to be very aware of just choosing who to put in the switchboard. So the key changes: clearance around switchboards, separation of switchgear, the date of initial energisation, again, which may just be a simple follow-up label to make sure that everything's compliant, and Appendix K, deemed to comply with 3439 or 61439, is probably going to be your biggest focus for compliance with switchboards. Thank you very much. Any questions? I get off nice and easy.
You do.
Oh, come on, Tony. We don't have time for all of your questions, by the way.
In regards to calculation, if you haven't got a test, heat rise test for a specific arrangement, and you can't get a heat rise test for something that's identical to what you're building.
Yep.
There's shifts, different sizes of breakers, different loads, etc. The existing software that was used by or given out by NHP and Schneider had a 4 partition limit,
That's correct.
or 3 partition. It might have been 4 compartments, 3
4
partitions.
compartments. Yep.
That's not practical, obviously. In most instances, you will have 7 or 8
That's
tier
correct. Yep.
stacks. I came across the problem where a client had a requirement to have an assessment on an existing switchboard, and the manufacturer had gone out of business. I talked to Peter Morris from NHP back then, and he says, don't use these for software because they're based on an IEC standard and they're not useful. So he gave me 2 pages out of a VDE book, and on that I started a spreadsheet,
Yep.
which I made a calculation. It involved some guesstimates because it was a weird switchboard. It had some funny vents and stuff. Is there any push or movement in regards to sorting out this 3 or 4 partition limit and coming up with decent heat rise calculation software where you can do a partial assessment at least, instead of having to test every single arrangement?
I think that'll be something that we might refer back to Rowan in the next one. Oh, would you like to answer? Oh, okay, fair enough. Well, I was going to say that one of the things in 60890 that's significant is that it talks about the temperature that it comes up with is an ambient temperature. It doesn't necessarily tell you what the temperature of the switchgear is.
This VDE gave you
Yeah.
So-
compartment by compartment.
So last month there was a meeting that I hosted in Canberra for the International Standards Group, MT2, and I'll just say publicly thanks for NESMA for supporting that, because they provided some funding to pay for morning tea and a few other functions to keep everybody happy in Canberra. One of those meetings was a 6890 task force. That task force is about 9 or 10 people. There are several manufacturers represented. Each of those manufacturers has been going away testing assemblies of various types against 6890 calculations. So what they've done is they've plotted what the calculation says, what they actually found when they tested it, and they're looking at how accurate is 6890, is it conservative, is it too conservative, is it not right? So the first step in that is to look at how does 6890 compare with what happens in the real world when we take these things to the test station. okay? And a lot of that, so VDE are part of that, right? A lot of that is about the origins of 6890 are a bit lost in time. You know, there's graphs and there's calculations and stuff in there.
90 requires that you have initial tests in order to
Yeah, but
calculate
the basis of it has been a bit lost in the history. So what's going on is the whole thing's being evaluated and saying, well, where do we want to go with this? So that's the international version. The Australian version's got a lot of content in it that Bill Johnson had a lot to do with, which was based on work done in Australia on tests. So some of that content will be relevant later on in that conversation. But right now, that's where 6890 is going. And whether it's limited to a number of partitions or sections or anything in the future, I don't know. But it is being validated against tests, again, the whole standard.
One of the difficulties there, Tony, is with too many different partitions, you start to lose the ability to calculate what's going to happen. There's lots of different considerations with airflow, eddying of airs around different terminals and its ability to take the heat out of a particular section. It's one of the reasons why we've got the Appendix N. That's a relatively conservative factor of copper bar ratings. From there, you've got additional calculation that can be done. You can do extrapolation from tests. So the way the standard refers to, if you've tested a 4,000 amp bus bar at so many square millimetres, you can draw a straight line from there back down to another known test and use that for your values in the middle. The reality is that if you did actual tests, you'd end up with a better rating out of the curves, and that's the intent of using these lower values to give you a more conservative amount. Any other questions? Thanks very much.